Okay, thank you very much. So, I didn't realise you'd amalgamated your intro slide. Okay, thank you very much. It's a pleasure to be here, and it's a great pleasure to be back at King's and the Institute of Psychiatry. So I'm a neurologist by training, and so I'm really interested in memory at times when memory goes wrong. And as you'll glean from the title, I'm going to argue that quite a number of disorders of memory are best understood as disconnections or as disorders of connection, rather than as some kind of loss of memories from some silo or some store. And that's not really a new idea. So these words, which I'll read out, these words were written in 1985 when I was probably trying to think about what O-levels to do. So a long time before I actually had any thoughts about memory. And this is from a paper published in 1985 saying I shall attempt to summarise the arguments in favour of a disconnection hypothesis, specifically that there are cognitive mediational systems subserved by frontal lobe structures that are disconnected from semantic memory systems subserved by temporal lobe structures. And this was a disconnection theory of memory based purely on the neuropsychological data at the time. And that was based on analysis by Elizabeth Warrington. So there's nothing new about the idea that memory and connectivity relate together and that memory disorders can be conceptualized as disconnections. The thing that is really new is the fact that we can now reconstruct connections that might be important in vivo in the living human brain. And the importance of this advance for neuroanatomy wasn't lost on the authors of Gray's Anatomy in its 150th year edition. And this is based on the work, of course, of Marco, Dominic and Derek Jones. So the idea that we can actually reconstruct these connections has very much reinvigorated this idea of connectivity disorders and disorders of memory. Now the technique that's allowed us to do that is diffusion tensor MRI. And I'll just gloss over what I think will be very familiar ground about how diffusion tensor imaging works. Diffusion tensor MRI is based on measuring the movement of water in brain tissue. And if you look at the diffusion of water in white matter, the situation is a bit like in this representation here. Water moves much more easily along the direction of tracts than it does perpendicular to the fibres. And that's because the myelin and the axonal membranes are barriers or hindrances to the movement of water. And we can measure that directionality as a property called anisotropy, and we can use that to build up images which tell us about the detail of white matter architecture. And this is an example of a fractional anisotropy image. And you can see this is also colour-coded to show which direction diffusion is along. So blue colour-coding here is diffusion going top to bottom in the brain, and these are the corticospinal tracts. Red fibres are the interhemispheric callosal tracts. And what we've also been able to do on top of diffusion tensor imaging is use this information to try and follow fibres. And what we do with this is that we look at the profile of water movement in a voxel, we infer that the fibre moves along this way, and then we take a step to the next voxel and continue to track the direction of these fibres until we build up a whole representation or a tractogram. And that's the technique that we call tractography. So this has really been the imaging revolution that's reinvigorated the idea of connections, structural connections, and brain disorders. Now, one of the things that I think is really good about having a clinical neuroanatomy seminar is it really refocuses us back onto the importance of anatomy. And one of the things about anatomy is we tend to know as much anatomy as we need to know, and in the last sort of 10 or 20 years in neuroscience, that's been enough anatomy to interpret blobs in fMRI. So anatomy at a pretty coarse level, mostly related to the cortex. So I'm going to go back a little bit to the anatomy of memory networks in the brain, and particularly what we know about connections that are important in the to memory in the brain. And that actually is really very important to interpret the results of the studies that I'm going to show later on. And really the most obvious source of information about memory networks in the brain comes from lesion studies. And the leading story from lesion studies related to memory is the hippocampal story. So this here on the right of the image, these are the representations of the lesions in the famous patient HM. And some people jest that the whole of memory neuroscience is based on the study of a single patient, which is an exaggeration, but certainly the studies of HM have been a major source of interest in the hippocampus and its relationship to long-term memory in the brain. HM is a patient who had bilateral medial temporal lobe resections for intractable epilepsy, and those resections certainly included the hippocampus on both sides. Now, the other source, of course, of information from lesion studies is that we can induce lesions in rodents and also, in fact, in monkeys. And we can also lesion the hippocampus in the rat brain. And in the rat brain, this is a much more impressive, sizable component of the brain. And in fact, across different species, through lesion studies that affect the hippocampus, we can draw out some consensus that it affects broadly similar mnemonic-type functions in the brain. But the hippocampus isn't an isolated structure in the brain. It's embedded in the medial temporal lobe. It's heavily connected to nearby cortical regions like the entorhinal cortex. And it's also intimately related with white matter. And in fact, macroscopically, it's closely related with this structure called the Fornix, which is a white matter tract fused to the fimbria in the tail of the hippocampus, which then curves forward and projects to the mamillary bodies. And so macroscopically, these two things are connected. Now, a lot of the information that we have about the connectivity of the hippocampus, like other structures, comes from tract tracing studies. And in fact, the tract tracing studies of the Fornix and hippocampus show that these are very tightly related anatomically. And this is an example of a retrograde tracer injection into the Fornix. And if you do this and follow the sites of labeling back in the hippocampus, in fact, you find a very characteristic staining pattern in the subiculum, presubiculum, and CA3 sector of the hippocampus. But the important thing is that these studies show that virtually all of the fibres in the Fornix arise from the hippocampus. It's an unusual example in that the two structures are very tightly related anatomically. And that relation between the Fornix and the hippocampus is important for reasons I'll come on to in interpreting some of the studies. Now, how can we really find out about the functional importance of these connections? Well, a bit like lesion studies, we can find out if they're functionally important just by transecting them, by cutting them and seeing what happens to function. And this is really one of the seminal studies of looking at the effects of Fornix transection in the monkey. Now, just to explain again, because this will be important later on, so what they did in this study, and this is the work by David Gaffin and the group at Oxford who really have been the leaders in this, was that they took monkeys and looked at their performance on a scene discrimination learning task. And in the unlesioned monkeys, they learn the scene discrimination quite quickly over 4, 5, 6 trials. And then what they did was that they sectioned a lot of the white matter of the temporal lobe, so the majority of the temporal lobe white matter in the temporal stem. And in fact, if you do that, the monkeys still learn this task reasonably quickly and are not very different from the unleashed monkeys. If you add transection of the Fornix to that, they end up with a dense impairment on this task, and their performance remains pretty much at the chance level across 8 learning trials of this task. So these studies show very clearly the functional importance of the Fornix for certain types of tasks that are very closely related to memory. Now those experiments that I've shown you along with others have led to this whole idea that the Fornix and hippocampus are part of an integrated network called the extended hippocampal network. And this starts in the hippocampus, projects via the Fornix to the mammillary bodies, and then via the mammillothalamic tract back to the anterior thalamic nucleus, and then the circuit is completed via the cingulum. And in fact, in a number of studies in rodents and monkeys, you can section or injure various parts of this core network, including the mammillary bodies or the anterior thalamic nucleus, and produce very similar, consistent deficits, suggesting that this works as an integrated core network for recollective memory. So this is the extended hippocampal network, which is one of the networks I'm going to describe. And as I've mentioned, a major white matter connection of the extended hippocampal network is the Fornix, and that's something that we can now reconstruct with diffusion tensor imaging, as I'll go on to describe. Before I do that, though, the other perspective to this to mention is the idea that there is not just a single network in the medial temporal lobe for memory. There are at least two networks which to some extent run in parallel. And the evidence for that is that if you damage the hippocampus or lesion it and you transect the Fornix, there are some aspects of memory which you leave intact. Particularly, you leave intact recognition to choose between two options. And the notion is that you can complete these tasks based on a different type of memory, based on a feeling of familiarity with the stimulus, where you feel you know that one is familiar, but you can't really recall any of the contextual details. So there is a separate system for familiarity-based memory. And in fact, if you produce lesions in other areas, like particularly the perirhinal cortex, you can produce the obverse pattern, where you selectively damage recognition memory with some retention of recollective memory. So there seems to be this double dissociation of memory systems in the medial temporal lobe, one of which is the extended hippocampal network, and the other of which is a network that supports familiarity mechanisms. Now, how are those regions connected with the rest of the brain? Well, we know that they're not connected to the rest of the brain via the Fornix, because we know that the Fornix is almost entirely generated from hippocampal projections. But there are a number of other parahippocampal tracts which connect the parahippocampal cortices to the rest of the brain. And there are two particular examples of that which we'll describe. One is called the uncinate fasciculus, and this starts in the anterior temporal lobe and parahippocampal region and curves forward into the orbital and inferior frontal lobe. And the other is called the parahippocampal cingulum, which projects backwards from the medial temporal lobe towards the posterior cingular region. So if we put this all together, I'm sorry for it's the neuroanatomy seminar, so I thought you'd enjoy lots of neuroanatomy, but just to summarise all of that, simply, we have this idea that we can reconstruct a number of connections from the medial temporal lobe to the rest of the brain. They are the Fornix, the uncinate, and the parahippocampal cingulum. And within that, there is this idea that there are parallel networks for memory. There is the Fornix hippocampus, extended hippocampal system, which is linked to recollective memory. And then there are the parahippocampal and perirhinal cortex, which are linked more by these other tracts, the uncinate and the PHC. And they're linked to familiarity and probably some other aspects of memory, including semantic contributions to memory and processes of meta-memory. So we get this idea that there are parallel networks that support memory in the medial temporal lobe of the brain. So I'm going to describe two studies where we take this approach, where we reconstruct these temporal association tracts, and we look at changes in the structure of those tracts and how those changes relate to memory. Just as a brief digression, before I do that, I just want to emphasise that this wasn't an entirely straightforward thing to do, and that there are a couple of things that we need to get across first in terms of the methods. The first is that the Fornix is not at all an easy target for diffusion tensor imaging. It's pretty small, it's strongly curved in its structure, and it runs quite close to lots of other major white matter projections, including the corpus callosum, which runs over the top of it and is orthogonal to it, with fibres going from left to right, and also anteriorly the anterior commissure, which runs between the anterior and posterior columns of the Fornix. So we've got this problem of curvature, and also that there are these crossing white matter bundles which generate crosstalk when you're trying to reconstruct. The second problem is that it's almost entirely an intraventricular tract. It's surrounded completely by cerebrospinal fluid, and that's the second problem, which I'll mention briefly in a moment. So to the first of those problems, the way that we got around that was that we used a tractography approach called constrained spherical harmonic deconvolution. Now, very briefly, what that does is, if you look at the water movement in each voxel, instead of just fitting one direction to it, it fits a whole three-dimensional profile, including more than one peak to the direction the fibres are going. So what that allows you to do is to model the idea that there are nearby fibres with a different direction that are crossing. You can just about see that in some of these voxels you have two orthogonal peaks. So the benefit of this is that it allows you to resolve one population of fibres from several others. So that was a real breakthrough, and that was very important in actually producing reconstructions of the Fornix which look realistic. Now, the second problem I mentioned is this problem of being surrounded by CSF. Now, this doesn't project brilliantly, but what this basically is a normal diffusion tensor sagittal image. You can see the Fornix as this little green structure underneath the corpus callosum. If you blow it up, what you find is actually the size of the Fornix is not sort of huge compared with the size of the voxels in the actual image. It's only sort of one or two voxels across. And the problem that gives you is, if you imagine this voxel here, you can imagine that most of that is filled with Fornix fibres. When we get to the edges, these voxels are sort of part Fornix and part water. And that really contaminates the measurements that you get from this through what's called partial volume error. So the second really key thing that we had to conquer to do this was to find a way to correct for partial volume error. And we did that with an algorithm called free water elimination, which was published about 3 or 4 years ago. So I just mentioned those two methodological hurdles, just to illustrate that the Fornix was a challenge, and there were a couple of important things to get across. So coming to the studies that we did two studies where we took this approach. We reconstructed the temporal association tracts, and we related structure in those tracts to memory. And we did that in two experimental designs. The first was that we looked at a group of healthy older adults, ranging in age from about 50 to early 90s. And that was to see if we could relate age-related changes in these connections to age-related changes in memory. And then the second experiment that we did was to extend that to a clinical group with a memory problem. So just to describe the age study first, we took a group of people from the normal community who had no memory complaints, were otherwise healthy, and we stratified them according to decade. And so we ended up with a group of 40 people with an average age of 68 and a range of about 50 to 90. All but 2 were right-handed. Now, as you might expect, this was quite a well-educated group with above average IQ. And this is simply a sampling and selection bias in the sort of people who are motivated to take part in studies. And so these were quite high-functioning individuals. We did diffusion tensor imaging on the scanner at Kubrick in Cardiff with a fairly standard 30-direction diffusion tensor imaging sequence. And then we did a whole range of cognitive testing, but with a real focus on memory. And so we looked at memory with several different tests, all of which included recall and recognition components. And we used various subscores of these tests to try and tease apart different components of memory. Now, the imaging, I've already shown you these reconstructions. This is an example of the 3 tracks that we reconstructed in one individual. The red structure here is the Fornix, the blue is the uncinate fasciculus, and the green is the Parahippocampal cingulum. And you can see that these all converge in the temporal Y matter and the medial temporal lobe. So these were the 3 tracks that we reconstructed. We measured diffusivity and anisotropy in these tracks by averaging the measurements for all points along the reconstructions. And we did some pilot studies to make sure that we could do this reproducibly. And I haven't shown that data, but these all produce things, intraclass correlation coefficients of above 0.97. So we can do this surprisingly reproducibly, in fact. And we corrected all of the measurements for partial volume errors. And these are the results of the association with age and structure in these tracks. And these are correlation coefficients both for anisotropy and diffusivity in the Fornix, uncinate, and Parahippocampal cingulum. And in fact, we find that although the effects, the association with age isn't uniform, actually there are age effects in most of the tracks that we reconstructed. Strong effects in the Fornix, but also effects in the uncinate singular. And this is a scatter plot of anisotropy in the Fornix against age, showing a fairly linear decline of Fornix integrity as people get older. So just to emphasize, these are healthy people with no problems with memory. And reassuringly, I think everyone I can see in the room is way over here somewhere. But the first thing that Professor Cowra pointed out when he looked at this graph is, I'm really worried. I'm actually on your curve. I'm not at the top of the Fornix relationship. So we find these strong relationships between multiple tracts and age. Now, when we looked at the relationships with memory, though, it was actually only the Fornix that came out as having strong relationships with memory performance. And Fornix related with memory across a range of measures from the different tasks that we used. In comparison, the uncinate fasciculus, although the uncinate shows age-related variance, we didn't find strong relationships between uncinate, microstructure, and memory. So the Fornix came out of this as being particularly related to memory performance. Now, digging a little bit deeper into this, we looked at this and said, well, actually, what if we covary out the effect of age from this relationship? And when we did that, we still found a significant independent association between Fornix, microstructure, and memory. So the implication from that was that the Fornix seems to contribute also to some of the inter-individual variability in memory that's not accounted for just by chronological age. And we also looked and thought, well, actually, is this all just because the older people have smaller hippocampal volumes, and this is all being driven by hippocampal inputs in the Fornix? And in fact, when we covary down a hippocampal volume from this relationship, we still find a significant independent association between Fornix, microstructure, and memory performance. And we don't find any convincing associations with any of the other tracts. So the main conclusion from that is that in the healthy brain, in older people, the Fornix seems to be a critical structure that relates to variation in memory performance in older people. And in fact, that goes along quite nicely with some studies in young adults done by the Oxford group, showing that Fornix microstructure relates to individual differences in performance in people in their 20s. So it seems that Fornix is the critical tract for recollective memory performance, and this persists into older age. So the next question we asked was, what actually happens in people as their memory starts to break down in older age? And the way that we did this was that we looked at people with amnestic, mild cognitive impairment. Now, these are people generally who attend a memory clinic, and they were all recruited from a Cardiff memory clinic. Amnestic mild cognitive impairment has various criteria attached to it, and a number of these patients go on to develop Alzheimer's disease. So in a number of patients, it's a prodrome for the development of Alzheimer's disease. So we took the view that because of that, in these patients, we know that their memory performance is impaired. We might also think that the extended hippocampal network is compromised in some way, because we know that hippocampus and Fornix structure are compromised in people with mild cognitive impairment. So we asked the question, when things change, when people start to develop memory difficulties, what impact does that have on the relationship between connections and memory? So just to run over the detail, this was a study of 25 people with mild cognitive impairment recruited from a memory clinic. We chose a subsample of the controls to match for age and IQ. So we subsampled the controls purely based on decade and their IQ score estimated by the NART. So we ended up with 20 matched control subjects, again matched for age, for sex and for handedness, with no significant differences in education or pre-morbid estimated IQ. Now we made a couple of modifications for this study. One of them was because in the meantime the Cambridge group, led by Peter Nestor, had looked at microstructural changes in mild cognitive impairment, and one of the things that they found was that the traditional measures from diffusion tensor imaging and isotropy and diffusivity don't really capture exactly what's going on in the white matter. And they also looked at two other measures called axial diffusivity, or diffusion measured along this long axis, and radial diffusivity, or the average of diffusion perpendicular to the long axis. And there have been a number of studies now that suggest that these two things have slightly different meanings, with the idea that radial diffusivity might relate more to myelination of tracts, and axial diffusivity might relate more to axonal processes. Now that's not proven, but they do seem to have differential relationships with a variety of things. So as a modification for this study, we added these measures to our DTI protocol. The other modification is very simple. We thought, well, we're now studying a clinical group. They don't have normal brains, they have something wrong with them. Shouldn't we actually look to make sure that the relationships between temporal tracts and memory are specific to temporal tracts? It's not just a sort of generalized brain rot effect. So what we did was that we also reconstructed the corticospinal tract as a control tract in those individuals. And the corticospinal tract measurements revealed no clear differences between group and had no relationship with memory. So I won't actually mention those any further. Now the first thing that we did was that we compared our control and our mild cognitive impairment groups. And in this, as expected really, we found that there are differences in the microstructure of temporal tracts between the groups. We confirmed that there seems to be some difference in Fornix structure between mild cognitive impairment and controls. In fact, the best measure of that was a measure called tissue volume fraction, which actually measures atrophy at the microstructural scale. So we found evidence that there was some subtle atrophy of the Fornix between these two groups. But in fact, when we looked at all of the other tracts that included the uncinate and parahippocampal singular, we found significant differences in both axial diffusivity and radial diffusivity between the two groups. So we confirmed that there's some problem with the Fornix in mild cognitive impairment, but we also found some subtle microstructural changes in the other temporal tracts. And then the next thing we looked at was we looked to see if we get the same relationship between Fornix structure and memory as we do in healthy aging. And this again, just as a reminder, this is on the y-axis, this is score on the memory task, on the x-axis, anisotropy with Fornix. And this is the linear relationship that we find in control subjects. Now when we looked at this in MCI, we found two things. As expected, they performed significantly worse at the memory task, but also we no longer really find a strong association between Fornix structure and memory in the mild cognitive impairment group. So although the Fornix is damaged in these patients, it doesn't seem to relate so strongly to individual patterns of memory performance. Now when we looked across the other tracts, what we found in fact was that we found a contrasted pattern or a dissociation in these relations. So again, this now is showing the correlation coefficients between measure of microstructure and memory for each of the tracts in the control group and the mild cognitive impairment group. And so you can see for the control group, the Fornix is most strongly associated with memory performance. In the MCI group, this is a much weaker relationship. But in fact, the converse we find for the Parahippocampal cingulum on the left. So here we find that there isn't much relationship in normal older adults, but in mild cognitive impairment, there's an emerging relationship between parahippocampal cingulum structure and memory performance. And these are the same results really represented in a different way. And this time what we've done is we've produced a montage of all of the tracts that we've reconstructed and colour-coded these tracts according to their strength and correlation with memory performance. And so here on the left of these images, we have the older volunteers. All that we really find is this red Fornix relationship, which is much stronger than the relationship with other tracts. In mild cognitive impairment, we don't find that at all as convincingly, but we do find relationships with unsnipped parahippocampal tract structure. And so the way that we've interpreted this is that in mild cognitive impairment, the Fornix is compromised, and we see some kind of shift in the relation between memory and tract structure. And one way to think about this is what might be happening as the Fornix is compromised is that you become more reliant on some other undamaged processes to complete these memory tasks. Perhaps think other processes like familiarity-based memory, or perhaps things like semantic contributions to memory. So it may be that there is a shift in memory strategy that underlies this relationship. The alternative is that there is some kind of recruitment of these tracts to support recollective memory. We don't know which of those alternatives is true. It's something that we need to investigate really in another design. But the idea that there is this shift, I think, is interesting. One of the things that comes from it is it makes you think that actually the vulnerability of the memory system to injury, say from a focal lesion, would change as somebody went from the normal aging pattern to the mild cognitive impairment pattern. And that's the hypothesis that's easy to test by looking at naturally occurring lesions, and also something that we're planning to do. Okay, so just to summarise all of that, there are a number of memory networks embedded in the medial temporal lobe. The extended hippocampal network is one we know most about, but there are also other networks that involve parahippocampal tracts that link the medial temporal lobe with other parts of the brain. We see age and disease effects across different white matter tracts linking the temporal lobe with other parts of the brain. In the healthy brain, it seems that it's the Fornix that's the critical tract for recollective memory. In people who've already developed a memory problem, there's some evidence of a shifting dependence on some of the ancillary non-fornical tracts. And so I'll finish there. I'll just acknowledge Claudia, who's the postdoc in Cardiff, who really led on these experiments, did all the hands-on work. Of course, Derek, who's instrumental in the methods that underlie all of this. John Addleton, who's provided the real neuroscience behind all of this for us. And also Laura Westacott and Jess Stevenson, who were PhD students who helped with some of the tract reconstructions. So I'll finish there and say thank you for asking me to come to the neuroanatomy seminar. We're now looking at the effects of stroke on these networks, and stroke's another area where people have largely forgotten about clinical neuroanatomy and correlative anatomy. So perhaps next time I can tell you a bit about that.
Thank you very much. Are there any questions? Yeah.
Thanks for a fascinating talk. Really interesting results I've got about the last experiment. Kind of mirrors what we've seen in other kind of related illnesses like construct aphasia, kind of other anatomically connected areas seem to compensate to perform the task. Can you go back to some of your some of the results that you showed?
Where would you like me to go?
Yeah, if you go, yeah.
Uh-huh.
I think it looks very likely, but you didn't actually test to see if the difference between the correlations was significant. It's actually the difference between the strength of the correlation for controls and the strength of the correlation for MCI. Fornix, is that actually the interaction? Is that significant?
That's a very good question. So I need to just.
I'd say it's probably because it's quite a big difference. Probably.
Yeah. I mean, just say I agree with what you first said about aphasia. I think it's true because the work that's coming out about for a long time has been this sort of debate about whether which of the two pathways is most important, and the kind of modelling work suggests that the parallel network model account better for the effects of lesion. So I think that where we're heading with this is parallel to the aphasia literature. So I agree with that. To answer your question, a very good question, but as you know, it's a very power-hungry thing to show a significant difference between two slopes. And if we do that, we don't produce it. And, we produce trends, but nothing we can hang our hats on. So I very much wish that had been the case. But for now, we just have to rely on showing the data as a scatter and showing it as a qualitative contrast.
MCI is obviously a quite heterogeneous group because obviously some of those people go on to develop Alzheimer's disease or be diagnosed with Alzheimer's or dementia 6 months to a year later. Some were. I'm just wondering whether there was any, whether you looked at, say, Fornix integrity, whether that predicted the onset of dementia or whether that's correlated with, the likelihood of developing dementia.
Yeah, there have been studies where people have suggested that it may be some kind of biomarker for future conversion. And in fact, I'll go back and I glossed over this slightly, but I think if you look at the relationship in MCI between memory and Fornix microstructure, you could definitely form the view that there are two groups in the MCI cohort. Now, in a sense, you'd expect that to sort of really weaken your chances of finding anything significant across the two groups, because the people with MCI who don't progress don't develop any other kind of pathology either on the whole. So you think that would weaken your chances, but certainly there's the impression that there are two groups in this. Now, we've started to look at this as a biomarker in some of the follow-up data that we have. Now, at the moment, it doesn't look as if it has a strong individual prediction effect. And as you know, even if you take something like hippocampal volume, which has been related to Alzheimer's disease strongly for years, if you take MCI cohorts and you measure their hippocampus on an individual level, it's a very poor predictor of conversion. Even though we do a group study, you see a really striking difference. Now, I think that the truth is the Fornix might be a bit better. Might be a bit better than that, but I'm still doubtful that it will really be useful at an individual predictive level. But at the moment, we've only got 2-year follow-up data on these patients, so our kind of conversion numbers are very limited. So it's a very interesting point. It may be useful, but I'm not sure which way it will go.
Just curious, it's only if it's a long time since I've been any of this. Did you manage to get trapped in every person you looked at?
Yeah, again, I mean, it's an important question, and yes, we did. One of the things that, in terms of the, again, I mentioned the digression about how difficult it was to do. And in fact, it was 2 years' work to really get the Fornix approach working reliably with the 2 additional methodological things that we applied. And when we first started doing it, we were very hit and miss. When we did it with tensor-based tractography, we got Fornix in about a third of the patients and nothing in the rest. But when we did the CSD approach, Dr. Brown's was right, we managed to reconstruct all of those patients. And also the scatter plots kind of suggest that there were no very gross outliers by the time we got to that point.
That's very nice.
So there was a lot of work behind that. I think one of the things about it also, though, is that I think there isn't very much burden of visible lesions in the medial temporal lobe, certainly not in the forelegs. And so maybe if you were trying to reconstruct other tracts where there's a lot more chance of vascular injury, it would be much more difficult. So maybe they'll be partly lucky by this focus on the MTR.
The other question was, have you looked at kind of functional activity between GFA and then you could correlate that with the measures you've got?
Yeah, I'd love to do that. I wish it was moving forward a bit quicker. And so we have resting state data of the same patients. And so we've been kind of busy trying to get the structural stuff done. So the MCI study has only just been accepted, actually. So we've got the functional connectivity measures derived now. We're just starting to look at. As you know, though, it's not that simple because you have to be really clear about your hypothesis and which connectivity measure you use, and if you use C's, where you get to place them, and how that relates to anatomy. And so we've been grappling with that sort of work.
You showed that the Parahippocampal singular is associated with some sort of declining compensation MCI, but only on the left side. What's your take on that?
Well, I don't have I don't have enough data to have a strong view on it. I mean, it's kind of provocative because it makes you think that maybe there's some hemispheric lateralization that's important. The results I showed, though, are from visual recall, so in a very sort of simplistic, visual versus verbal way, you can't really tie them together with that. And I don't know, because it's with the numbers that we have to start contrasting across hemispheres with memory, it's pushing the power of the study a bit. I think one of the ways to address it is going to be to look at lesions, though, because then that's a more powerful design. If we start to look at lesions of left and right PHC, and how that relates to changes in memory, that might help.
Did you look at the dynamic interaction at all? So feasible for predictions we do have?
That's the second question. Is a very good question, I think. I mean, we have tried with this DTI algorithm. I don't think it's feasible in terms of terms of having resolution in that region. We've tried in Norway, we've been able to legally reconstruct. But one of the big problems is you need seed regions of interest that are very anatomically precise. You can sort of draw those on high quality T1s, but really to applying that back to your low resolution DTI images is simply not quite difficult. So Sarah is trying very hard to do that. So with a modified DTI sequence, and that might make it simpler. What would you predict? I'm not sure. I mean, I think it's. I'm not sure in the animal models of Fornix section whether you see secondary changes in MMT structure. So I guess if I wanted to find the answer to that, I'd probably talk past John or go back to the papers and see if you see that sort of transsynaptic effect. And see, I don't know. What do you think would happen?
Well, if it's to my view, if it's part of the same group or symmetry, then maybe you have the same associations.
I mean,
If you're positive into a symmetry system.
I mean, of course, Sarah and that work, one of the things they have done is looked at people with Fornix injury from colloid cysts, and in fact, they have shown that online getting body atrophy secondary to that. So I guess if you imagine the projections from the Lewy body are affected to, you imagine you can see a similar relation.
The second question goes back to why did you say further on before my time? But the technical stem hypothesis which we've got discredited as the system. And did you consider looking at the technical stem? What's your technical motivation to
Well, I think that's a really intriguing question. I think that the Parahippocampal singular probably runs through the temporal stem or those projections run through the temporal stem. So my take on it is that one of the reasons that the effects of temporal stem lesions are inconsistent across species and across studies is that there may be this change in background where the importance of the PHC in those connections varies depending on what's happening in the rest of the network. So I think the bottom line is that there is this, inconsistency. The temporal stem hypothesis in monkeys is really holding up. Whereas most of the support for it comes from studies of human stroke. So I think it may be that there's this dynamic background that's influencing what you see in those regions. I don't know if that sounds
Okay, that's it. Thank you.